Hey everyone. This next section is going to be part of the Force Dynamics unit, but it's a new enough topic and it's a little bit hard to describe until you learn more about it. And so we're going to play a little guessing game with this to try and help you understand the wide variety of types of this new thing, okay, this new topic. All right, so what do all these pictures have in common? Play along with me here. All right, so you got that giant balloon, anchor truck or a car that looks like it got stepped on by King Kong. I'll be able to come back to all of these and tie into one concept. All right, the former student, hockey player Rito, giant wall of Marshall stacks. Former student high jumping or not high? Yeah. Long jumping. All these have something in common here. So units of the thing we're talking about are kilograms meters squared per second squared, believe it or not. All these different things to recap here. All right, let's keep going. Let me know if you guess, you guess. So they should start getting more obvious now. Got sources of heat there, I guess, right? Windmills, solar panels, usually classes in person have guessed by this point, certainly at this point. This is a type of electrical generation station where they have a bunch of mirrors that reflect sunlight up to this spot, and it gets so hot it boils water, makes steam, and makes electricity. And nuclear power generation, that might actually not be nuclear power generation. That might be just a cooling towers from just even coal burning, but possibly anyways, I'm not sure. So we figured it out. It is lots of what being released. So in this case, I'll come back to these, I guess. I'll get to it soon here. So pretty much you're probably thinking energy at this point, right? Especially when you get to this one. So the concept we're talking about is energy. So the source of all of it on Earth, at least, except for nuclear and geothermal, I suppose, is from the sun. So all our forms of energy, except for nuclear. So you could say even like fossil fuels are from the sun, right? Because it's from plants and organic material that absorbed energy from the sun a long time ago. And so energy is what we're trying to get you to think about here, right? So if we go back to start here, obviously we're talking about like energy stored in food. So it's like chemical potential energy stored in food. We're going to talk about the different forms of energy, right? And so we have wind energy, and so you're going to get motion, energy of motion, or called kinetic energy from the wind. Picture the energy stored in this giant balloon. If it were to pop, you'd have a lot of pressure stored up as elastic potential energy, the stretch of the rubber, the latex. Here, this was a truck, a tanker car that was being heat pressure cleaned, and so it got really hot as part of all the cleaning, and then they closed it up for the night and went home, and the pressure inside dropped because the hot air had expanded, and then they closed all up, and the hot air, of course, cooled down, and the motion of the particles slowed down, and the pressure decreased, and then the atmospheric pressure around it pushed in too hard and crushed the thing. It's kind of a crazy thing. I do a demonstration in my science class of can crush demo. You might have seen it where you take a pop can of any sort and heat it up and then put it into water with the open end first, and it cools off really fast, and it has a rapid cooling and rapid contraction of the air molecules and crushes the can. We've got like the energy of the punch here, energy transferred. And so we're going to be talking about force times distance. So picture the force and the distance that the person is being pushed there in each of those cases. We've got sound energy here, so energy from pressure and kinetic energy of molecules. We've got energy due to height, so that's gravitational potential energy. All these types of energies we're going to cover soon. Some kinetic energy, obviously, too, in that one. Mostly gravitational there. You're almost stopped at the top there, of course, ideally. So the fundamental units are kilograms meters squared per second squared, and we'll see why. The named unit, they call that the joule, kind of like calling kilometers per hour your speed, except it's named after a person. And then, of course, we got energy due to heat or chemical potential energy being released to make thermal energy. So heat is a transfer of thermal energy, so we really should say thermal energy.
Keith Gilbert, the office, please. Keith Gilbert, the office.
And we got wind energy, obviously, being converted to electrical. So you got wind, and then we could put on there that it's getting converted to electrical, of course. So you hear the word potential used a lot. So it's like stored energy or energy that's available to do work. It's referred to as. And so we end up with electrical potential energy. And obviously here, solar energy. So we're getting energy from solar, and again, converting to electrical potential energy. Let's copy that thing. So again, just starting to appreciate and notice all the forms of energy around in the world around you is the goal of all of this. All right. So this, like I said, possibly is nuclear potential energy. I'm gonna add the word energy there. Nuclear potential energy, and again, converting to electrical potential energy. And so one of the big things we're going to see is the idea of like conversions of energy from one form to another. So I'm trying to emphasize that. Obviously, here you have a giant explosion, a release of energy there. Here we can really analyze here where we have water that's up high here, and so it is has gravitational potential energy, and then it of course comes out as kinetic energy and gets converted to electrical potential energy, or just electric energy. And then of course you've got your electrical energy coming into the house. You've got the different form of energy, obviously here. It's energy in advertising. It's not actually energy concept as much. More alertness, I suppose, right? I guess you get the energy from like the massive amount of sugar that's in this kind of drink. So yeah, there's energy there too, but the caffeine addiction portion of it is a little different. So we're thinking energy, right? And so types of energy, we have kinetic energy and we have potential energy. And so kinetic energy is energy due to motion. And so mechanical energy, sound energy, all those types of things we've been talking or looking at. And the potential energy is energy that is stored. So chemical energy, elastic potential energy, electric potential energy, gravitational potential energy, all those things, okay? I really do think of kinetic energy as possibly being stored energy as well. If you have an object that's moving, it has kinetic energy. You can have a system where like cars have flywheels that spin as part of the engine, and it's like stored energy to help keep things spinning in times when there's not enough energy, and so on. But the official definition is potential energy is this, like stored forms, and then kinetic energy is when you release this potential energy. It's what they think of it as, right? So the mechanical energy of an object is those two things added up, okay? Kinetic plus potential. So I'll do this. And just put a plus sign between there. That is the total mechanical energy of a system combination. I guess I should put an equal sign here. All right, so let's start with basics here. So I found this picture online, and any Rideau students might be able to guess what teachers I often say these kind of look like. Kind of looks like Mr. Furlotbush and Mr. Sleath for any Rideau students. But anyways, it's not actually, it's just a Google image. But when we're talking about energy, the fundamental definition of energy is work done by a force, and it's the force that you can tell was applied and the distance over which the force was applied. It's really just force times distance. All right, so work done, or W or delta E. Okay, work done is a transfer of energy. Okay, so that's first thing to recognize, that you can use W and delta E very much interchangeably. Call it work, or work done. Those all just mean the same thing. We're talking about energy transferred. Okay, so delta E is very much that particular wording there, right? And so really, when you're talking about a change in anything, as always, it's final minus initial, right? And so we're just talking about change in energy, and we're not talking about vectors here, right? Of course, we're just talking about value, like the amount there is. You can have increases and decreases, but it's not actually a vector. We're not putting vector signs over that. So work done is the change in energy is what we're saying here, okay? And so on the previous page, I talked about how the basic definition, the most fundamental definition of energy transferred and work done is force times displacement, right? So that is understood to be a multiplication. These are vectors. And so just to deal with that in an official way, there's a particular kind of multiplication of vectors you would have heard about in math class, or will hear about in math class, called the dot product. And you'll see why I'll show you here right now, I guess, but if you're applying a force at an angle, there's a component of that force in the direction that it goes. We know this from our previous unit, right? And so if you have the x component of the force times the x displacement, then you get the work done. And so what's officially described as the dot product as in math class, they just describe it as it's a version of multiplication of vectors. It's a definition to do with multiplication of vectors. That definition comes from reality around in the world around you, the idea of work done by a force. And it's specifically work done by a force at an angle to the displacement, right? And so how these become not vectors is in the definition of the dot product. It's actually the magnitude of each of those vectors. Magnitude just means the size, right? So it gets rid of the directions. The direction is dealt with by the cosine of the angle. You can tell it's cosine because they're adjacent, okay, based on that arrangement of the vectors. So we talked before about how the units are, where's my units thing here? Units. Yeah, there we go. Kilograms meters squared per second squared. And we'll see why pretty easily here based on that fundamental definition. And so we're talking about force times distance, which is mass times acceleration, F equals ma, right? So ma, so force is in newtons. And because newtons is mass times acceleration, you can say that's kilograms meters per second squared. So kilograms for the mass and meters per second squared for the acceleration, since force equals mass times acceleration. And then we have another mass, or another meters, sorry. And so meters times the meters gives us the meters squared. And so, yeah, we have kilograms meters squared per second squared pretty easily from that definition. That is what's defined officially as the joule, or capital J for the symbol for it. For the units anyways, I should say. Right? So, yeah, only the force in the direction of the displacement contributes work done. If you're at a large force at an angle, only the force in the direction of motion actually causes acceleration, as we know from the previous unit. So it's the only one that's increasing your speed, and that increase in speed leads to the increase in kinetic energy. So it's your transfer of energy. It's your work done. Okay. All right. So some details about this, situations when work is done and also when it isn't, right? So we're looking at when energy is transferred and when it isn't. And so only the size or the component, obviously, of the force in the direction of motion contributes, like we said, right? So only that counts for work done. And so in this situation here, you've got your applied force at an angle, and so just that component counts for work done if the displacement is straight sideways. So I should add in here the point about how the acceleration in the x direction, so ax depends only on fax, right? So applied force in the x direction, acceleration in the x direction. And so the change in kinetic energy, so I don't know if we can do that quite yet, but basically extra energy due to motion depends only on fax as well, right? So just to justify why, of course, the idea is pretty obvious, right? The acceleration is in the x direction, and so only the component of the force in the x direction is contributing to that acceleration. Pretty obvious stuff, I think. Just needs to be known and pointed out and just obvious, so you can use that concept, right? Which will lead us to cases where no work is done. Okay, so if there's no energy transferred, right? So we don't end up with any extra speed. We don't end up any extra energy of any kind. We don't end up with any extra speed. We don't end up with any extra height. Like if you're lifting water up, right, it ends up with extra gravitational potential energy. So that would be a transfer of energy. If you're pushing on something sideways and it goes faster and faster, you're contributing energy to the system. You're adding energy. Right, so you've got a delta E equals some positive value. And so if there's no force in the direction of the displacement, then there's no work done. And if there's no displacement, okay? So if you're pulling an object really hard but it doesn't move, then no work gets done. If you don't have a force in the direction of motion, so it's back here. All right, sorry about that. So if you're carrying wood, you're just holding it at a certain height and just walking with it sideways with constant motion, then you know that you have no net force in the direction of motion. You're not accomplishing any new work. You're not accelerating the wood. So like once you have lifted it and once you have got going, you walk for a kilometer with it, you're not actually contributing any energy to the system, and so there's no work being done. There was work lifting it, you can give it gravitational potential energy, but then of course you set it back down, all that energy comes back out, right? So as frustrating as it is, if you're moving a pile of wood from one location to another, you're not contributing any energy to it at all overall. So really, you're not accomplishing any physical work. You've moved it to where you want it, and of course, it was hard work to do it for the human body, but you're just working against friction and so on, right? So if you keep going with this, like this person's pushing on this piano here, and it's obviously hard to do that, right? You're pushing it along, but the person's not lifting it, so there's no new gravitational potential energy. It's not speeding up, so there's no new kinetic energy. But obviously, there is work done in this situation, right? There's a force times a displacement, right? And so you don't have any new energy in the system, though. So where's that extra energy end up, right? So there is work done in this case, but where did the energy end up? Well, it actually dissipates into the universe, kind of thing. It ends up as thermal energy due to friction, right? So where this wheel was pushing on the snow, it would have like melted a little bit of the snow there and stuff like that. Like if you rub your hands together, obviously you can feel the thermal energy. So yeah, cases that look like no work is done, but there is. So it looks like no work is done because there's, you're not ending up with any new energy that's visible or usable. But we did do work there. So there are cases where there's no work done, but you think there is. There's cases where there is work done, but you might think there isn't. And yeah, so energy is a little bit elusive to pin down. So you got to be cautious of that and very deliberate on your analysis of things. Okay. If you look at force versus displacement graphs, area is force times displacement. And so if you have constant force or if you have a changing force, right, either way you can get areas. And so area equals work done. So let's do that. Area equals F delta D, which equals work done. Just as a little brief intro to something you'll see later on if you go on in this field of math and physics. If you don't have constant forces, then you can actually approximate the area underneath with a bunch of rectangles, right? This is basically was done for a while before Newton came along and invented calculus. But basically, you could approximate, and you can get a better and better approximation the narrower the rectangles are. So if you're going to try and approximate the area of a circle, I've done this in math class where I have a circle on a piece of graph paper, and you add up all the little squares as best you can, and then you say, okay, well, maybe these 3 squares add up to another square, and or this one and this one add up to a square. You just basically try to approximate that area. You'll find the finer the smaller the size of the grids, the better your approximation, right? So Newton went one step further and said, okay, we can actually automate this process. We can make it a mathematical process. And so he figured out the link between the equations. Say this was a quadratic equation, or this is the equation of a circle. He figured out the link between the equation of the circle and how to mathematically do this. And so there's symbols here that are easy to understand if you think of it once you've told what they mean. So this just means the limit as the size delta x goes to 0 is what that says. It's a little scribbly. But as this size goes smaller and smaller, right, you're adding up E, and you might have seen it in spreadsheets, and that just means summation, right? It just means add up all the, right? So you're going to add up all the rectangles. This is a force times the displacement, right? A force of F delta x. So add up all of those rectangles is what that means. You get your area, right? And so adding up all your rectangles get your area. And then this part says, well, let's take the limit of that. In other words, see what value that approaches as we get smaller and smaller rectangles. And so when you put that together, all of this limit of the sum of all of the rectangles, they just write as this symbol here, which is called the integral. What I'm talking about is integral calculus, which you'll see in like first year university math. And if you take math in university, you take calculus, right? In the high school calculus course, we do the derivative or differential calculus, which is all about slopes. And then integral calculus is all about areas. But really, the idea is this mathematical treatment of determining exact values for what an area would approach or what a slope would approach. The slope version that you'll see in high school calculus is basically if you take the slope of that line, missed a little bit there. I probably can't. I don't know, whatever, close enough, right? But you take the slope of that, and then you take a slope of that, and then you take the slope of that. You can tell the slope is approaching a particular value, and it's approaching the slope at a point. Basically, eventually, you get these points going so close together that you have a tangent like that, and if we start to call it a tangent, and it becomes a slope at an instant. Anyways, so a little bit of an aside there mathematically, but I feel like if you have an idea of what the math is for, then when you go to learn it later on, it might make it a little bit easier to master and understand. All right. So one last thing here. I'm going to test the copyright police here, but credit given to Veritasium, this site here that we're going to play the video from, and the links there for the video and everything. So we're promoting his channel really, so I don't think he minds. But the question is, we're talking about energy still, right? As part of this lesson, obviously, right? And so the question is, what do we get from the sun? So I'm going to play the first 2 minutes, then I'm going to skip a little bit through the middle, and then I'm going to play the remainder because there's a word here that is it's a weird word. It's hard to understand, and it's very often misunderstood by many, including me. But I think this video does a pretty awesome job of showing or helping understand what it is. So let's load up a video here. Let me just pause quick. I'll make sure to get that running. All right, here we go. Got the video queued up and timestamps here, so here we go.
This is a video about one of the most important, yet least understood, concepts in all of physics. It governs everything from molecular collisions to humongous storms, from the beginning of the universe through its entire evolution to its inevitable end. It may, in fact, determine the direction of time and It may, in fact, determine the direction of time and even be the reason that life exists. To see the confusion around this topic, you need ask only one simple question. What does the Earth get from the sun?
So what does the Earth get from the sun?
What does the Earth get from the sun?
Well, it's light rays.
What do we get from the sun?
Warmth.
Warmth, light.
Vitamin D. We get vitamin D from
You get vitamin D from the ultraviolet rays?
Well, a lot of energy.
What does the Earth get from this energy?
Yes, energy.
Energy.
Nailed it. Every day the Earth gets a certain amount of energy from the sun. And then how much energy does the Earth radiate back into space relative to that amount that it gets from the sun?
Probably not as much. I don't believe that it's just radiating right back.
I'd say less.
Less. I would Less. say less.
I guess about 70%.
It is a fraction.
I'd say 20%.
Because we use some of it.
We use some of the energy.
We consume a lot, right?
But the thing about energy is it never really goes away. You can't really use it up.
It would have to break even, wouldn't it? Same amount, yeah.
You know, cause and effect, it'd be equal in some ways, right?
For most of the Earth's history, it should be exactly the same amount of energy in from the sun as Earth radiates into space.
Wow.
Because if we didn't do that, then the Earth would get a lot hotter. That'd be a problem.
That'd be a big problem.
So if that is the case,
Yeah.
then what are we really getting from the sun?
It's a good question.
It gives it us a nice 10.
It gives us a nice 10. I love it. We're getting something special from the sun.
I don't know. What do we get without the energy?
Nobody talks about it.
To answer that,
So yeah, what are we getting really? It's not energy because energy is staying about the same over time, right? Otherwise we'd be overheating or whatever. The next section here, like I said, I'm going to skip through a little bit, but they talk about a person named Carnot and the Carnot engine. So you just need to know like the basic idea, but it's called a heat engine. So I'll skip through it a little bit here.
we have to go back to a discovery.
So we don't
on
need the
December
history
30th.
lesson here.
Father was not only a general,
So let me
but
just
real
skip ahead a bit.
military might of nations depended on having the best steam engines.
So it came about because
But
of
French
research
designs
to do
were
with improving steam engines.
falling behind those of other countries, like
And-
Brit heat engine would work. One with
So-
no friction and no losses to the environment.
So basically, they got all scientific, right? And they looked at the theory of heat engines. And so they had the idea of an engine that would work on getting pressure from a block of steel that has thermal energy, and it would increase the pressure and so on, right? And it would basically transfer energy between hot blocks and cold blocks, and in theory, it would transfer back and forth without losses. One sec here. All right, sorry about that.
And they don't transfer heat at constant temperatures.
So
Became less
keeping going
usable.
here.
Energy is most
Oh,
usable.
one sec.
This
I need to go
process
to
is
852.
irreversible. Radiated heat, which is up
Here we go. Sorry about that.
into
All
the
right.
cold bar. So not all the energy stays in the flywheel. Now, in Carnot's
And again, we're working on what the answer is for what we're really getting from the sun, right?
time, high-pressure steam engines could only reach temperatures up to 160 degrees Celsius. So their theoretical maximum efficiency was 32%, but their real efficiency was more like 3%. That's because real engines experience friction, dissipate heat to the environment, and they don't transfer heat at constant temperatures. So for just as much heat going in, less energy ends up in the flywheel. The rest is spread out over the walls of the cylinder, the axle of the flywheel, and is radiated out into the environment. When energy spreads out like this, it is impossible to get it back. So this process is irreversible.
Double check.
The total amount of
recording here.
energy didn't change, but it became less usable. Energy is most usable when it is concentrated, and less usable when it's spread out. Decades later, German physicist Rudolf Clausius
So
studied
basically, the answer to the question ends up being that we're getting more concentrated energy from the sun. But what the heck does that mean, right? So this is what prompted basically scientists to think about this and come up with the basic laws of thermodynamics and how energy really works. And it ends up relating to even the passage of time itself, the direction of the passage of time.
Carnot's engine. And he comes up with a way to measure how spread out the energy is. He calls this quantity entropy.
That's the
When
answer.
all the
by
energy
way.
is concentrated in the hot bar, that is low entropy. But as the energy spreads to the surroundings, the walls of the chamber and the axle, well, entropy increases. This means the same amount of energy is present, but in this more dispersed form, it is less available to do work.
So high entropy means spread out, not useful. Low entropy means concentrated energy that's useful to do work. Okay.
In 1865, Clausius summarizes the first two laws of thermodynamics like this. First, the energy of the universe is constant. Second, the entropy of the universe tends to a maximum. In other words, energy spreads out over time. The second law is core to so many phenomena in the world. It's why hot things cool down and cool things heat up, why gas expands to fill a container, why you can't have a perpetual motion machine, because the amount of usable energy in a closed system is always decreasing. The most common way to describe entropy is as disorder, which makes sense because it is associated with things becoming more mixed, random, and less ordered. But I think the best way to think about entropy is as the tendency of energy to spread out. So why does energy spread out over time? I mean, most of the laws of physics work exactly the same way, forwards or backwards in time. So how does this clear time dependence arise? Well, let's consider two small metal bars, one hot and one cold. For this simple model, we'll consider only 8 atoms per bar. Each atom vibrates according to the number of energy packets it has. The more packets, the more it vibrates. So let's start with 7 packets of energy in the left bar and 3 in the right. The number of energy packets.
So a hot bar and a cold bar, just like in the Carnot's heat engine, right? And so they're thinking about this. They're thinking about the ideas of this, right?
It's in each bar is what we'll call a state. First,
Energy
let's consider just the left bar. It has 7 energy packets which are free to move around the lattice. This happens non-stop. The energy packets hop randomly from atom to atom, giving different configurations of energy. But the total energy stays the same the whole time. Now let's bring the cold bar back in.
That's in an isolated system, right?
Only 3 packets and touch them together. The energy packets can now hop around between both bars, creating different configurations. Each unique configuration is equally likely. So what happens if we take a snapshot at one instant in time?
So because the motion of the particles and the transfer of energy from between the particles is random, then all of these combinations are equally likely. Okay?
And see where all the energy packets are. So stop. Look at this. Now there are 9 energy packets in the left bar and only 1 in the right bar. So heat has flowed from cold to hot. Shouldn't that be impossible because it decreases entropy? Well, this is where Ludwig
So that'd be
Boltzmann
more concentrated energy, right, in that bar. So that should be impossible because it would break the second law of thermodynamics, right?
made an important insight. Heat flowing from cold to hot is not impossible, it's just improbable. There are 91,520 configurations with 9 energy packets in the left bar, but 627,264 with 5 energy packets in each bar. That is, the energy is more than 6 times as likely to be evenly spread between the bars. But if you add up all the possibilities, you find there's still a 10.5% chance that the left bar ends up with more energy packets than it started.
So that does still, you should see that, right? So why don't you?
So why don't we observe this happening around us? Well, watch what happens as we increase the number of atoms to 80 per bar, and the energy packets to 100, with 70 in the left bar and 30 in the right. There is now only a 0.05% chance that the left solid ends up hotter than it started.
So it's a mathematical thing, right? It's a probabilities thing. The number of combinations where the energy went from cold to hot is very small in comparison to the number of possible combinations where the energy evens out, right? The most obvious, common, most probable state is when the energy evens out.
And this trend continues as we keep scaling up the system. In everyday solids, there are around 100 trillion atoms and even more energy packets. So heat flowing from cold to hot is just so unlikely that it never happens. Think of it like this Rubik's Cube. Right now, it is completely solved, but I'm going to close my eyes and make some turns at random. If I keep doing this, it will get further and further from being solved. But how can I be confident that I'm really messing this cube up? Well, because there's only one way for it to be solved, a few ways for it to be almost solved, and quintillions of ways for it to be almost entirely random. Without thought and effort, every turn moves the Rubik's Cube from a highly unlikely state, that of it being solved, to a more likely state, a total mess.
So that's the same for the heat combinations, right? There's just only one way, well, very few ways for it to go from cold to hot, but just an unimaginably big number of ways for it to go the other way.
So if the natural tendency of energy is to spread out and for things to get messier, then how is it possible to have something like air conditioning, where the cold interior of a house gets cooler and the hot exterior gets hotter? Energy is going from cold to hot, decreasing the entropy of the house,
making it more concentrated, right? More the temperature gradient's getting greater, colder versus hotter, colder inside in comparison to hotter outside, which is the opposite of what should naturally happen.
Well, this decrease in entropy is only possible by increasing the entropy a greater amount somewhere else. In this case, at a power plant, the concentrated chemical energy in coal is being released, heating up the power plant and its environment, spreading to the turbine, the electric generators, heating the wires all the way to the house, and producing waste heat in the fans and compressor. Whatever decrease in entropy is achieved at the house is more than paid for by an increase in entropy required to make that happen. But if total entropy is constantly increasing, and anything we do only accelerates that increase, then how is there any structure left on Earth? How are there hot parts separate from cold parts? How does life exist? Well, if the Earth were a closed system, the energy would spread out completely, meaning all life would cease, everything would decay and mix, and eventually reach the same temperature. But luckily, Earth is not a closed system because we have the sun. What the sun really gives us is a steady stream of low entropy, that is, concentrated, bundled up energy.
The energy that we get from the sun is more useful than the energy we give back. It's more compact, more clumped together.
Plants capture this energy and use it to grow and create sugars. Then animals eat plants and use that energy to maintain their bodies and move around. Bigger animals get their energy by eating smaller animals, and so on. And each step of the way, the energy becomes more spread out.
Okay, interesting.
Yeah.
Oh, wow. I did not know that.
There you go.
Ultimately, all the energy that reaches Earth from the sun is converted into thermal energy. Then it's radiated back into space.
But in fact, it's the same amount. I know this is
You do know this is.
I'm a PhD physicist.
Even think about like decomposition of organisms. It produces heat, right? It just dissipates energy back out into the universe.
Okay.
Well, anyway,
I trust
so-
you.
The increase in entropy can be seen in the relative number of photons arriving at and leaving the Earth. For each photon received from the sun, 20 photons are emitted. And everything that happens on Earth,
So you get high energy photon comes in, and then 20 low energy ones go out. It's spreading energy out, literally.
plants growing, trees falling, herds stampeding, hurricanes and tornadoes, people eating, sleeping, and breathing, all of it happens in the process of converting fewer higher energy photons into 20 times as many lower energy photons. Without a source of concentrated
Those low energy photons are just heat, just energy dissipating, right? That's what he's talking about.
energy and a way to discard the spread out energy, life on Earth would not be possible. It has even been suggested that life itself may be a consequence of the second law of thermodynamics. If the universe tends toward maximum entropy, then life offers a way to accelerate that natural tendency. Because life is spectacularly good at converting low entropy into high entropy. For example,
So we take useful energy and radiate it out as not useful energy, right?
well, the surface layer of seawater produces between 30 to 680% more entropy when cyanobacteria and other organic matter is present than when it's not. Jeremy England takes this one step further. He's proposed that if there is a constant stream of clumped up energy, this could favor structures that dissipate that energy. And over time, this results in better and better energy dissipators, eventually resulting in life. Or, in his own words, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant. So, life on Earth survives on the low entropy from the sun.
And that quote is more substantial than people might think, right? You're thinking, oh, there's a seed there and it produces a plant. He's not saying that. He's saying that the low entropy, clumped up, usable energy that comes in would cause there to be structures form that help convert that usable energy into a spread out version. So convert low entropy to high entropy. And so it starts with molecules, like nitrogen, for example. Nitrogen gets fixed by the lightning, which means it ends up getting converted into other components or compounds that are found in DNA. And so, like these molecules start to help convert low entropy energy to higher entropy, and then life molecules are formed, and eventually, life exists. Is essentially what they're saying. Weird.
Where did the sun get its low entropy? The answer is the universe. If we know that the total entropy of the universe is increasing with time, then it was lower entropy yesterday, and even lower entropy the day before that, and so on all the way back to the Big Bang. So right after the Big Bang, that is when the entropy was lowest. This is known as the past hypothesis. It doesn't explain why the entropy was low, just that it must have been that way for the universe to unfold as it has. But the early universe was hot, dense, and almost completely uniform. Everything was mixed, and the temperature was basically the same everywhere, varying by at most 0.001%. So how is this low entropy? Well, the thing we've left out is gravity. Gravity tends to clump matter together. So taking gravity into account, having matter all spread out like this would be an extremely unlikely state. And that
and unlikely means low entropy, right?
Is why it's low entropy. Over time, as the universe expanded and cooled, matter started to clump together in more dense regions. In doing so, enormous amounts of potential energy were turned into kinetic energy. And this energy could also be used, like how water flowing downhill can power a turbine. But as bits of matter started hitting each other, some of their kinetic energy was converted into heat. So the amount of useful energy decreased, thereby increasing entropy. Over time, the useful energy was used. In doing so, stars, planets, galaxies, and life were formed, increasing entropy all along. The universe started with around 10 to the 88 Boltzmann constants worth of entropy. Nowadays, all the stars in the observable universe have about 9.5 times 10 to the 80. The interstellar and intergalactic medium combined have almost 10 times more, but still only a fraction of the early universe. A lot more is contained in neutrinos and in photons of the cosmic microwave background. In 1972, Jacob Bekenstein proposed another source of entropy: black holes. He suggested that the entropy of a black hole should be proportional to its surface area. So as a black hole grows, its entropy increases. Famous physicists thought the idea was nonsense, and for good reason. According to classical thermodynamics, if black holes have entropy, then they should also have a temperature. But if they have temperatures, they should emit radiation and not be black after all. The person who set out to prove Bekenstein wrong was Stephen Hawking. But to his surprise, his results showed that black holes do emit radiation, now known as Hawking radiation, and they do have a temperature.
I love that his goal was to prove it wrong, and instead he listened to the science evidence and the information he found and changed his mind, right? He's like, oh, actually, it's right.
The black hole at the center of the Milky Way has a temperature of about 100 trillionth of a Kelvin, emitting radiation that is far too weak to detect, so still pretty black. But Hawking confirmed that black holes have entropy. Bekenstein was right. Hawking was able to refine Bekenstein's proposal and determine just how much entropy they have. The supermassive black hole at the center of the Milky Way has about 10 to the 91 Boltzmann constants of entropy. That is 1,000 times as much as the early observable universe, and 10 times more than all the other particles combined. And that is just one black hole. All black holes together account for 3 times 10 to the 104 Boltzmann constants worth of entropy. So almost all the entropy of the universe is tied up in black holes. That means the early universe only had about 0.000000003% of the entropy it has now. So the entropy was low, and everything that happens in the universe, like planetary systems forming, galaxies merging, asteroids crashing, stars dying, to life itself flourishing, all of that can happen because the entropy of the universe was low, and it has been increasing. And it all happens only in one direction. We never see an asteroid uncrash or a planetary system unmix into the cloud of dust and gas that made it up. There is a clear difference between going to the past and the future. And that difference comes from entropy. The fact that we are going from unlikely to more likely states is why there is an arrow of time. This is expected to continue until eventually the energy gets spread out so completely that nothing interesting will ever happen again. This is the heat death of the universe. In the distant future, more than 10 to the 100 years from now, after the last black hole has evaporated, the universe will be in its most probable state. Now, even on large scales, you would not be able to tell the difference between time moving forwards or backwards. The arrow of time itself would disappear. So it sounds like entropy is this awful thing that leads us inevitably towards the dullest outcome imaginable. But just because maximum entropy has low complexity does not mean that low entropy has maximum complexity. It's actually more like this tea and milk. I mean, holding it like this is not very interesting. But as I pour the milk in, the two start to mix, and these beautiful patterns emerge. They arise in an instant, and before you know it, they're gone, back to being featureless. Both low and high entropy are low in complexity. It's in the middle where complex...
So low complexity at the beginning of the universe and low at the end, but in the middle where we are right now is complex and interesting, right?
Structures appear and thrive. And since that's where we find ourselves, let's make use of the low entropy we've got while we can.
There we go. So mostly, just relax, because mostly what we're focusing on is just energy. But I just felt I couldn't not talk about focusing on energy, but I couldn't not mention entropy because the two go hand in hand. And it's it's your first kick at the can of getting a feel for what entropy is. And there's that quote about life basically being favored by the entropy concept itself. So we have entropy, kinetic energy, potential energy, the basic work done definition, and so on. And I still have to actually make these work pages for you. So I'll get that set up and put this out. But so we're talking about energy, but we also mentioned entropy. So there you go. Yeah. All right. Talk to you again soon. Thanks for watching.